Hello everybody, my name's Ben Kinberg, and today we're going to be talking about the difference between displacement and total distance traveled. This is a confusion. People get these mixed up a lot when they're learning calculus, and so here's a lesson on how to differentiate the two. Things you're going to need for this lesson: you're going to need one, basic knowledge of integration rules. To complete this lesson, you should definitely know how to do a definite integral. You need to know what the graph of a derivative means. You're going to need can-do spirit and maybe some paper if you want to take some notes. So first, I think it's helpful to talk about just the differences between displacement and total distance traveled, just because, they come up in the same question sometimes and they are very similar. Displacement is the net distance traveled. So let's take example, we've got Ted here. He travels 8 feet to point A, 10 feet to point B, another 10 feet to point C, 20 feet all the way over to point D, and then 10 feet back to his initial position. Seeing as this is the net distance traveled, it doesn't really matter how far Ted went on his journey, forward, backward, in the negative direction, over this way, or in the positive direction over this way. He ended up in the same place, and so our net displacement is going to be 0. So if you end up in the same place, it doesn't matter how far forward you go or how far backward you go, your displacement is 0. Displacement is like self-improvement. The destination matters. In that, I mean, you can buy as many self-help books as you want. You can read the 7 Habits, How to Win Friends and Influence People, all sorts of books out there. But if you don't change your habits and you don't get to a new point in your world of self-development, then you've really accomplished nothing. Just like Ted here, how he's gone on this long journey and then come back to his initial position and accomplished nothing. So if I have a point on a line and it travels so far this way towards the positive direction, and then it again gets here and then travels so far this way into the negative direction, then its displacement would be the positive direction and the negative direction combined, and you would get your net value for how far this particle moved, just as we got our net value for how far Ted went. Total distance traveled is another beast, and it is easy to remember because it's just like it sounds. It's the total distance that you travel. So say instead, Ted, of walking this distance, he were to have taken a car with a mileage gauge on the dash. I forget what that's called. But he would have tracked how far he went. He would have had some device. And it would have tracked the 8 feet walking this way, the 10 feet walking this way, the 10 feet walking this way, and so forth. And when he returned to his initial position, that mileage, that total distance travel, would read 58 feet. That is the 8 feet plus 10 feet plus 10 feet plus 20 feet plus 10 feet. That would be the total distance traveled by Ted. So at the end of the journey, Ted here would have completed 58 feet. Right? Doesn't matter if it's in the negative direction or the positive direction. Total distance traveled just cares about how many feet you managed to travel on your journey. So the total distance traveled in this case would be 58 feet. Lovely. And I like to think of total distance travel like a good road trip. It's about the journey. The destination doesn't really matter. If in this case we take this particle x, it can journey this far forward and that far backward. We would take the absolute value of the distance here, and we would just add it to this, and you would get your total distance traveled. In the case of this particle x, the displacement is likely negative, right? And the total distance traveled is likely positive. Because, again, total distance traveled just takes into account the amount of distance a particle is moving on a line, whereas displacement has to do with where your x is on that line. Okay? So now it gets to the fun part. We're going to apply this to calculus. Apply to calculus. We have a example problem here. The motion of Marvin Gaye's tour bus on tour through a one-dimensional line can be described with the following velocity function of time. V of t equals 3t squared minus 18t plus 24. Find the total distance traveled by the Prince of Seoul and his net displacement at the end of the tour. So from t equals 1 to t equals 5. So it would be helpful to start with what we know about total distance traveled so far. And we know that total distance traveled, because we're being asked for this in our problem, is it's at least you're moving. So no matter how far Marvin Gaye and his squad of musicians move on the journey, they're moving. So it doesn't really matter if they're going in the positive direction or the negative direction. Eventually we're going to graph this function, and you'll see that at a certain point in the prince's journey, he's going through the negative direction below the x-axis, and total distance of traveled will account for that in a positive way, because at least you're moving. At least you're going somewhere. It doesn't matter if it's the wrong way, at least you're going, and so to total distance traveled, that of course counts. Whereas displacement, where are you headed? This is this is your hippie aunt versus your stern mother. Your hippie aunt will say, "Oh, it doesn't matter what college you go to or what major you're going in. At least you're moving. At least you're getting somewhere." Whereas your mom, she cares about where you're going. She wants you to go to Princeton. She wants you to, major in health science or whatever. She cares about your destination. So here we have an integral. We have a velocity here, and we know that the integral of velocity with respect to time is position, and that's what we're looking for, because total distance traveled and displacement both have to do with position. All right, we're going to be integrating this velocity function. So knowing what we know, that distance traveled accounts for all motion in a positive way, we can use absolute value to find the total distance traveled. Even when we're going in the negative direction, we want to account for that in a positive way, just like your hippie aunt. She doesn't care if you're making bad decisions, at least making decisions at all. Whereas displacement, where are you headed? This is your mom, who takes your losses as losses and cares about your bad decisions. So she will take into account you traveling in the negative direction as a negative thing. So here we have the formula to find displacement at point B. We have to take this integral on an interval. So from A to B, in this case, it's going to be from 1 to 5. And you take the function in question, v of t, which we have here. You plug it into your calculator, and you're going to get an answer, right? Total distance traveled is a little more nuanced, right? You've got your interval here from A to B, but you're going to take the absolute value of the function v of t. This is because it doesn't matter how negative or positive you're going to be. At least you're moving, right? So you're going to account for your motion in the negative direction as positive. So here we have this function up here, Marvin Gaye's rad tour bus, graphed. We know that integrals are the area beneath the line, or from the line to the x-axis. So we have here, this would be our positive. This is when Marvin is moving with the bus in the positive direction from what looks like 1 to 2. He moves in the negative direction in this area from 2 to 4, this area here. And then in this area, again, it's a positive move from 4 to 5. So we can see that they go forward for a certain amount of time, they change direction at 2, and then change direction again at 4. And we know this is a quadratic, so we have our trough here. So we know this is quadratic. So let's solve these integrals using these formulas, and we're going to do it by hand, because in the 1970s, Marvin Gaye did not have TI-84s. So we've set it up here, displacement. We've got from 1 to 5, 3t minus 18t plus 24t d of t. Don't forget this bit here. People who forget that bit suck. Next, we are going to integrate this expression. You know how to do this. You have t cubed minus 9t squared plus 24t. This is just, your good old exponent rule. Now we're going to 1, 2, 5, and we are going to 5 cubed minus 9 times 25 plus 24 times 5. I'm running out of room. It's okay, these things happen. Minus at the bottom, so it's going to be what, like 1 minus 9 plus 24. I did this in a calculator and I know that it's 4. So this is going to be your displacement. Just a regular definite integral, doing what we know, applying what we know about the area underneath the curve. So you take the positive area here and the positive area here, you're adding them up, and then you're subtracting this negative area, and you're going to get your displacement. Next, we're going to have to talk about the total distance traveled, and not using a calculator makes this a little bit more difficult, yes, because I could, of course, just plug this into my calculator, and I'll get the correct answer, which, by the way, is 12. Spoiler alert. But thinking about this as a single expression can get kind of complicated, and I'd rather not do the whole thing with the absolute value bars. It might be more helpful, and it was for me when I was doing this problem, to think about this in 3 different integrals, right? Because you really only need to take the absolute value of this section of the graph, and since we have it here exposed to us, we might as well break it up so you know that from. And you can figure all of this out with just an interval chart. And that from this section to this section, from 1 to 2, we are positive. From 2 to 4, we are negative. And then from 4 to 5, we are positive again. And we know that from our knowledge of quadratics and basic common sense that this area is the same as this area. So what can we do with that then? We can actually split this interval up into 3 different intervals. From 1, oh my god, looking at this through my camera. From 1 to 2 of v of t, d of t, yes, plus from 2 to 4 of the absolute value of v of t. Remember, we're doing total distance traveled. So it does not matter that this section of the graph is actually negative, that Marvin and gang are actually traveling in the opposite direction, because total distance traveled only cares that you're moving. And so we're going to account for this motion in a positive way through these absolute value bars. We're going to add also this section again from 4 to 5 of v of t, d of t, which of course is the same as this section. And solving all of these, you will find that the answer is 12. All right. You know that we can actually solve all of these definite integrals, which I have done. It's not quite as neat as the other ones, but the work is there. You can plug all of these into the calculator, but we're going to do them for funsies. From 1 to 2 of 3t squared minus 18t plus 24 d of t. Now the integration is the same, and what we're really doing is this integral here and this integral here, just to save time. And that will give me, if I do the math, just as we did up here, we're applying the same process, I'm going to get 4. So this is really 4, and this is also really 4. So let's look at what we've done so far. If we know that subtracting this from these two things is going to give us 4, then we can conclude that this is also 4, and that we adding them all up can get 12. But you can also do this definite integral to get the answer 4 as well. So the answer is 12. And that will be our total distance traveled. So remember that total distance traveled accounts for all motion positively. Displacement counts for negative motion in a negative way, and then you'll be on your way to Flavortown, making sure that you do all of these problems correctly. Thank you for watching. I hope that this has been helpful, and yeah, with integrity, Ben Kinberg.